Hello everyone, hi, it's Daniel again. Good to see some of you here, some familiar names. Welcome to the last lesson of the Mathspace Academy. So you might have got an email this week letting you know that this is the last lesson that we're going to be doing, mainly because everyone's going back to school. So as of next week, we expect that most students will be back in school, learning back in the classroom again. So there's not much of a need for this anymore as there was a couple of weeks ago when all the schools were closed and we had a lot of students at home needing something like the Mathspace Academy to help them out with their studies. But now that you'll be back in school on Thursdays at 10 a.m, you won't really be able to come to this anyway. So that's why we've decided to finish this up. We were planning to go for the whole term, but since all the states in Australia have decided to go back sooner, that's why we're going to finish a little earlier than we expected. But for those of you who've been here since the very first lesson, thank you all for coming for all this time, and thanks again for joining me today. So I'll do a proper goodbye at the end, but let's get started with the very last lesson. And so today's lesson, we're doing scale factors and similarity, okay? And so we're going to be looking at this concept of similar figures. So for the very last time, who am I? My name is Daniel O'Kane. I'm a maths teacher. I work at this company called Mathspace. I've created thousands of work example videos that are available in Mathspace's online textbooks. And I've got many years of teaching experience, both online and in the classroom. So as I always start, just to let you know that what we do today obviously doesn't cover a whole week's worth of work in 1 hour. This is more of a summary lesson, okay? But I want to give you enough of an understanding so that you can go away, and if you've learnt this in class already, then great. Hopefully you've really walked away with a proper understanding of the topic. And if you haven't done it in class yet, when you do see it in class later, you'll be able to hopefully follow along a lot easier. Okay, so I'm going to continue to follow along with the Mathspace curriculum. So we've worked through the algebra and indices chapter. We've worked through a Pythagoras' theorem chapter. So today we're starting on this scale and similarity chapter. So this class will be recorded. So the recordings that we've done over the last 8 weeks, they're all going to still be available online for any of you who want to watch them. So even when we stop teaching the academy, we've still got those 8 recorded lessons at each of the year levels from 7 to 12. So as usual, I'll be asking questions today and hoping that you reply to me in the chat box. So it's a really good chance for you to engage with me as I'm going through today's class. And if you've got any bigger questions, you can leave them in the Q&A section of Zoom, and I'll leave some time at the end of the class to answer those questions. And because it's the last lesson, ask me whatever you want, okay? I mean, obviously be respectful, don't be cheeky. But yeah, you can ask me anything about the maths that we've covered, not just today. You could talk about anything that we've done in the last 8 weeks. So today's lesson is on scales and similarities. So we're going to be looking at this concept of scale factors to explain similar figures and also study the specific conditions required for triangles to be similar. So we look at triangles specifically, especially right-angled triangles, because then we can link that to Pythagoras' theorem, what we've done previously. And I'll also talk a little today about trigonometry as well, okay? Just so that once you do learn trigonometry in class, hopefully this understanding of trigonometric ratios will be more clear to you as well. So what are we doing today? It is scale factors and similar triangle tests from chapter 4 of the Mathspace textbook. And so next week, well, there will be no next week, as I mentioned. So it is the end of the Mathspace Academy. Today is the last lesson. So at 10 a.m. next week, please don't come back because I won't be here, okay? So as usual, if you want to do any further study beyond what we cover in this 1 hour, okay, you can come to wootube.mathspace.co, and after today's lesson, you'll be able to open up chapter 4, scale and similarity, and you'll be able to watch Eddie Wu's videos here. So you can see there's 11 videos on scale factors, similar triangles, and also what we won't do so much of today, which is scale and area, how it affects area measurements, okay? So you can go ahead and watch all those videos to get a deeper understanding of the topic. So, similar figures. So 2 figures, okay, are similar if they have the same shape and the corresponding dimensions form the same ratio, okay? So looking at this particular question, okay, here are 2 rectangles, okay? And so they have the same shape. They're both rectangles, okay? And now their corresponding dimensions form the same ratio. In other words, 5 times 2 gives 10, okay? And then 2 times 2 gives 4, okay? So because that length and width of the first rectangle is both doubled, you get this similar rectangle. You can also think of it as like an enlarged triangle. So it's still got the same length to width ratios, okay? It's just that they're different sizes, but you can still call them similar rectangles. If they had the exact same measurements, so if they were both 5 by 2 rectangles, you could call them congruent rectangles. And congruent is a word in geometry that we use that means the same, okay? But when the dimensions are in the same ratio, that's when we refer to them as similar figures, okay? Right, clear the board. So a scale factor, when we talk about scale factors, when we talk about similar figures, a scale factor, which normally in textbooks you'll see referred to as the letter K, it can be found so that it multiplies all the lengths in one shape to create all the lengths in the other similar figure. So when mentioning that example that I just looked at before, okay, this scale factor was 2, okay? So the 5 was multiplied by 2 to create 10, and the 2 was multiplied by 2 to create 4. So K equals 2 is the scale factor that was used to create the second rectangle, okay? In other words, the first rectangle was enlarged by a factor of 2, okay? And so when you talk about the area of this shape, okay, I'm not covering a lot of this in today's lesson, but for the area, well, I know that would be, if I draw this just on my screen, the area would be 2 by 5, so 10 square centimeters for the first rectangle. The second rectangle is 40 square centimeters, 10 by 4, okay? So with the scale factor, okay, you don't multiply the area by 2, you multiply the area by 2 squared, okay? So it's actually K squared times the first area, okay? And that's how you can use scale factors to also find the area. So although the dimensions have been enlarged by a factor of 2, we can see the area is increased by a factor of 4, 2 squared in this particular case. All right, I think we now should do some practice. Let me just double check. Actually, before I do, let's talk about what we saw in Pythagoras last week and the week before. Okay, so remember I proved using algebra, okay, that if that Pythagorean triad ABC exists, and you multiply each of those lengths by a scale factor K, you prove that Ka, Kb, and Kc also form a Pythagorean triad. So we saw that proven using algebra. Okay, if you use now geometry, okay, well, right-angled triangles are similar figures, okay, when they have those specific ratios. So looking at this basic example, okay, so 5, hold on, let me just draw on the screen. So multiplying this by 2 creates the 10, multiplying this by 2 creates the 8, and multiplying this by 2 creates the 6. And so that means that they're similar figures, and if they're similar figures, then those internal angles in the triangle are going to stay the same. And so if those internal angles stay the same, then of course this is still going to be that right-angled triangle. So then that means no matter what measurements you have, okay, you could have A, B, and C, and you multiply by a scalar factor K, you're just producing a similar figure that would also be a right-angled triangle, and therefore it would have to satisfy Pythagorean theorem, right? The sum of the squares of the shorter sides would equal the square of the hypotenuse. So that's another way to prove that what I mentioned last week about that scale factor K, creating a new Pythagorean triad when you look at the multiples of Pythagorean triads also being Pythagorean triads. So that's just like a little bit of a bonus from last week. Okay, so what I'm going to do now is we're going to go through some examples. And so we're not going to prove similarity yet. What we're going to do is just assume that the shapes are similar and then talk about similarity a little more and, you know, finding scale factors. Okay. So in this question, determine whether each statement is true or false. Are all circles similar? So every possible circle with every possible radius, are they all similar shapes, true or false? So I want you to write the answer in the chat box. Okay. So I'll give you all a couple more moments. So the answer is actually true. So if I look at a circle, okay, the circle is a special shape where there's only one dimension, right? It's just that radius from the center to the outer edge. Okay, so let's say this is a circle of 1 centimeters and this is 1.5 centimeters, okay? Well, this radius can be multiplied by any scale factor to create another radius, right? Even if it was like 2 and 2.2, there's always that number that you can multiply by 2 to create another number. So yes, all circles are indeed similar, okay? So I could use a hint if you're a Mathspace user to help you answer this question. And so the hint actually says any circle can be scaled up or down to create another circle. And because it's the one dimension, yes, that's true. So I can say option A, all circles are actually similar. Are all squares similar? True or false? So squares also just really only have that one dimension, right? That one side length. So remember, the square is a special type of rectangle where all the side lengths are congruent. They're all the same length, okay? So then that means, just like with the circle, okay, you can multiply that side length by any scale factor to create another side length. So then that's true, right? A square, okay, you can either increase its size or decrease its size. You can enlarge it or you can shrink it, but it'll still have those same internal angles, and it's only the one measurement that you're changing, okay? So then yes, all squares are indeed also similar. Okay, what about all isosceles triangles? Would all isosceles triangles be similar? Yes, true or false? So, if I draw an isosceles triangle like this, so these angles are quite large. Let's call them 70 degrees, 70 degrees. So then what would you have left? 40 degrees, right? So that all the angles add to 180. Okay, these two sides would be congruent. Okay, but then that base length can be different. I can draw a different type of an isosceles triangle, because remember that definition of isosceles is just the two congruent side lengths. Okay, and then those base angles are the same. So I could have 30 degrees, and that could be 120 degrees. So these are not similar triangles. We can see that because those internal angles have changed, I don't have 40, 70, and 70 anymore. I have 120, 30, and 30. Those are two examples of isosceles triangles, and isosceles triangles can have different angles inside. Okay, they still all add up to 180, and you still have the base angles being equal, but those angles, as those base angles change, so will the angle up top, right? And so then these congruent side lengths therefore have different ratios. So the ratio of this length to this length is different in this case compared to this case, right? So then those ratios aren't the same. So actually this is false. So isosceles triangles, when you group them all together, they are not all similar. There is a special type of isosceles triangle that's similar. We'll talk about that in a moment, but no, that is a false statement. Okay. What about all equilateral triangles? Are all equilateral triangles similar? True or false? Okay. Well done, Remy. Yes, this one is true. Okay. So with an equilateral triangle, that's a special one, remember. Okay. So an equilateral triangle is where all three side lengths are congruent. They're the same length. Okay. And then all those angles are 60 degrees. So if you've got an equilateral triangle where all the side lengths are 10 meters, for example, and then you look at a bigger one, it's still got those same angles. Equilateral triangles always have the same 3 equal angles of 60 degrees. Okay, the side lengths are always going to be congruent no matter what equilateral triangle you look at. The only thing that changes is that one measurement, right? Just like a square and a circle, okay? That one measurement, I mean, that's easy. You're multiplying 10 by 2. But I could have 10 and 11, right? So why don't we do that? Because some students don't realize that. I could have 10 meters and 11 meters. Okay, and you might think, well, how can you multiply 10 to get 11, right? Scale factors don't have to be whole numbers, okay? So I could multiply 10 by, in this case, 11 over 10, this fraction, right? So that 10 times 11 over 10 creates that 11. Those 10s just cancel, right? So a scale factor doesn't have to be an integer. It doesn't have to be a whole number. So in this case, because it's that one measurement that we're multiplying, okay, I mean, all 3 side lengths are the same, so they all get multiplied by 11 tenths to create 11, okay? So yes, all equilateral triangles are in fact similar. So we can say that statement is true. What about all right-angled isosceles triangles? Are they similar, true or false? So remember in part C, we found that not all isosceles triangles are similar, but what about right angle isosceles triangles, true or false? Okay, so I'm waiting for one person. Yep, great. Remy, having a guess? True, question mark? Yes, it is true. Well done, Remy. So a right angle isosceles triangle is special because it's got that right angle. Okay, so it's going to have those 2 equal lengths and then the longer hypotenuse. Okay, now the thing about a right angle isosceles triangle is that I know those base angles, remember, are equal. So that's going to be 45 degrees and that's going to be 45 degrees. So then even when we enlarge by a number, okay, so if you look at, 2 and 2, for example, and I look at maybe a larger triangle where it's maybe 2.2 and 2.2, okay, you're still multiplying these values, okay, by a scale factor to create these values, all right? And because this is a right angle triangle, okay, whatever the hypotenuse is also going to be multiplied by k to create a hypotenuse of that same length, right? And I know that's the case for a right angle isosceles triangle because for the right angle isosceles triangle, okay, those angles stay the same, all right? So that's another way to remember what similar shapes are, especially with triangles, okay? For triangles, those angles, those interior angles will always stay the same, okay? So 45 degrees. So that's why it is true, Remy, that all right angle isosceles triangles are in fact similar. Okay, so that's just looking at a few different types of shapes to determine whether they are similar or not. So that's something that you can go away and remember. That way, if in a test or something they ask you, they give you 2 squares, for example, and say, are these similar? You don't have to do the scale factor working it out. You can automatically say yes, because all squares are similar. Okay, let's move on to the next question. Okay, so now determine the scale factor between these two circles in the diagram below. Okay, so we know now from the last question that all circles are similar. Okay, so if they're all similar, then how do I create a scale factor to go from a diameter of 15 to a diameter of 75? Okay, does anyone know what number I would then multiply? So you don't have to look at the radius of the circle, okay? You can look at the diameter of the circle, okay? And have that as the one dimension in the circle. So I'll give you all a moment just to answer this. So what I'm trying to find is, I know because circles are similar, that the diameter of 15, if I multiply that by a scale factor, okay, it is going to create the other diameter, 75. So I'm trying to find that value of K. Yes, correct, Sumia. Sumia's just told me the answer. It's 5, okay? So if you didn't know that, thank you, Remy. Yeah, I can also see you got the answer too. Well done. So dividing both sides by 15 in this equation will give me that enlargement factor. So that enlargement factor I could write as 75 divided by, using the division symbol, 15. And then that is going to be, of course, 3. So, whoops, 5. I got that wrong. Yeah, there you go. So yeah, multiplying 15 by 5 gives you 75. So then the first circle has been enlarged by a factor of 5, okay, to create the second circle. Now, as is the case in this question, you won't always get diagrams to scale, okay? So if I look at this line, it is obviously not 5 times smaller than this line, okay? So this diagram is not to scale. You're not always going to get your diagrams to scale, okay? So I do want you to note that as you start answering your own questions about this, okay? Because, to draw a circle of this size to then draw another one 5 times bigger, it takes up a lot of space on the page. And so, people who create these resources like tests or textbooks, for example, they don't want to waste so much paper actually giving you a circle to scale that's 5 times bigger. So do note that not all your diagrams, when we talk about scale factors, are going to be actually to scale. Okay, all right, we can go to the next question. We'll do a couple more of these. So now we're looking at these 2 rectangles, okay? And we're told that they are similar, okay? So those dimensions are going to have that same ratio. So the smaller rectangle, its length and width will be multiplied by a scale factor, the same scale factor for both length and width, to create the length and width of the bigger rectangle. So the smaller rectangle is described by these vertices A, B, C, and D, okay? So I can see A, B, C, and D. And then the larger rectangle is W, X, Y, Z, described by these vertices, W, X, Y, and Z, okay? So to find that scale factor, and if you know the answer, please feel free to write this in the chat box before I tell you, okay? You can just, using the Cartesian plane, calculate those lengths and widths, okay? So using, I can see that on my Cartesian plane, I've got this 1 scale factor, so going 5, 6, 7, 8, 9, 10. 5, 6, 7, 8, 9, 10. So every division on the vertical and horizontal axis is 1. Okay, so that's going to make it easy for me to count. All right. So if I'm going from -4 on the x-axis to +4 on the x-axis, okay, for that larger rectangle, I'm going this distance of 8 units horizontally. Okay. And then it's a similar way to work this out for the the top length, okay, along the y-axis, okay. You're going from this, okay, which is 4 below 10, so that's 6 to -4, okay. So then we have this length of the large rectangle being 4 plus 6, 10 units. Now, looking at the smaller rectangle, I'm going from -2 to 2. Okay, so that smaller rectangle has the width of 4 units. Okay, and because I know these rectangles are similar, I'm told in the question, okay, well, you can work out that 1, 2, 3, 4, 5. I've got this height of 5. Okay, so a 4 by 5 rectangle that's similar to an 8 by 10 rectangle, it's easy to see that both those dimensions in the red, the 4 by 5, have to be multiplied each by 2 to create the 8 by 10. So then what's that scale factor between the two rectangles? It is 2, okay? Or you can work this out by taking the height of the first rectangle, 10, and dividing by the height of the second rectangle, 5, okay? And because the two rectangles are similar, you can do that for the height, or you can do it for the width. So I know that the larger rectangle had that width of 8, and I can divide by that width of 4. Okay, so both of these create the same scale factor, this scale factor of 2. So well done, Remy, for writing that answer correct in the chat box. Okay, so just zooming out now. And I can go to the next question. We'll do 1 or 2 more of these similar figure questions, and then we'll move on to similar triangles because that's a little harder, okay? All right. So considering this diagram, okay, so I've got these 2 triangles, and the question asks me, are these shapes similar, yes or no, okay? So I've got these triangle with dimension, the small ones, dimensions 4, 5, and 7. And then the larger triangle has the dimensions 8, 10, and 14. So are the shapes similar? Remy has answered yes. Okay, let's find out. So remember, all 3 dimensions have to be multiplied by the same number, okay? So 4 multiplies by 2 to create the smallest measurement on the second triangle. 5 multiplies by 2 to create 10 on the as the second largest measurement on the larger triangle. And then 7 multiplies by 2 to create that measurement of 14 on the second triangle. So all 3 measurements are multiplied by the same number, that same scale factor of 2, to create the larger triangle. So then, yes, it has to be similar, okay? All the dimensions will be multiplied by the same scale factor, and they're both the same shape, they're both triangles, so that satisfies this definition of similar figures. So yes, these are similar figures. Gesundheit, pardon me. Okay, so then what is that scale factor? Well, we worked that out to determine that they were similar. The scale factor was 2. So then that question is complete. Okay, looking at these triangles, okay, that we are told specifically that the triangles in the diagram are similar. Okay, so you know already from the question, it tells you that the 2 triangles are similar. Okay, and so we've got these matching 3 angles, all right? So it's easier in this question because both triangles are orientated in the same way, okay? But these angles become very important when they're orientated in different ways, okay? Because triangles can still be similar if one is just rotated around, because the definition of similar has nothing to do with the level of rotation. It's just, you know, are those side lengths in a corresponding ratio, and are they the same shape? So I can see this angle matches this angle. This top angle matches this angle because it's got the 2 lines, and then the third angle's got the 3 lines. So those are corresponding equal angles, okay? So first, what is the scale factor? So you can determine that from the base length, okay? And so Remy has answered that correctly, that the scale factor must be 3. So if I multiply that 5 by 3, I get 15. Okay, and so I know those are the corresponding lengths in the same ratio because of the way those angles are orientated. So I know that number is 3, 15 divided by 5 is 3. That's the scale factor. Okay, so now we can use the scale factor to solve for x. So again, I believe Remy's actually already answered this. So then I just need to multiply this dimension, okay, by 3 to get this dimension x, okay? So then x has to be equal to that scale factor of 3 multiplied by the 3 centimeters. So x is going to be 9 centimeters. So that's correct, Remy. So yeah, that's how you can now use this concept of similar figures to help you find missing dimensions. All right, very good. All right, let's see if we've got one that's a little harder, and then maybe we'll go on to similar triangles. It's pretty easy. Yeah, this one's a little hard. Let's do this one. Okay, so we're told now these two triangles are similar. Okay, so we already know they are similar, and so I can see that this angle matches this angle. This angle matches this angle, and because triangles always sum to the same amount, right, 180 degrees, I know automatically that this angle has to equal this angle. Okay, so we've got those 3 angles that are the same, so I know these triangles are similar. Okay, but I'm already told that in the question already. I'm just double checking. Okay, so now I can determine what that scale factor is to find the value of g. Okay, because I know that the side length between the green and yellow angle, okay, must correspond to this. Okay, that side length again between the green and yellow angle. All right, so this is being multiplied by a scale factor, okay, to get 42, right? So if 7 times k is equal to 42, that means k must equal to 6, right? Because 6 times 7 is 42. So that scale factor is 6, so we can use that now to find g. No, we can't. I can use it to find f, but not g. Oh no, yes I can. Yes, I can. Yeah. So actually, I read that wrong. We can. So that means this 5. Okay, it is the angle opposite. Okay, that green. It's the side length opposite that green angle. So then if I look at the angle opposite that green angle, that's the g. That's what I want to figure out. So that means 5 is going to multiply by that scale factor 6 to create g. All right. So that means then g is going to equal scale factor 6 times 5. Okay. And so Remy gave me that correct scale factor of 6, great, and then wrote that g is 30. Well done. So yeah, g is then going to have to be 30. Now I can find the value of f in the original triangle, okay? Because f sits between the green angle and the unknown angle. All right, and then this here sits between the green angle and the unknown angle. Okay, so then these are the corresponding side lengths. So then f has to multiply by 6 to get 30. So 6 times f is equal to 30. So yes, Remy, that's correct. You found the answer of 5. Okay, so f would have to be that dimension 30 divided by that scale factor 6. So you don't always multiply by a scale factor to find a missing dimension. Sometimes you've got to take the larger dimension and divide by the scale factor to find the smaller dimension, in this case 5. Okay, so note these triangles were actually isosceles triangles, okay? So this dimension and this dimension were the same side lengths, okay? And then so this dimension and this dimension were the same side lengths. So actually, even though they're labeled as different angles, they actually have to be the same angles. They're actually, these are two isosceles triangles. Because remember, an isosceles triangle has those two congruent side lengths. So that means those corresponding base angles must be congruent as well. Okay, so even though they're labeled differently, they're technically the same angle. Alrighty, let's see, we'll do maybe one more harder one of these, and then we can move on to the similar triangle tests. Yeah, this is a good example. This is the one I was thinking of. Great, okay. Alrighty, so here's a really interesting question. All right, Ryan wants to find the height of his office building, okay? And so you can do that with a mirror. So you place a mirror flat on the ground, and he's done so 10 meters from the base of the building. And so if we're told if he stands exactly 0.63 meters away from the mirror, he can just see the top of the building when he looks directly into the mirror, okay? And then we're told the triangles formed by the reflections in the mirror are similar. So if Ryan's eye level is 1.76 meters from the ground, what is the height of the building? Okay, so you have to look at this diagram with these two triangles that get created. So you've got this triangle and this triangle, okay? And so we're told that these two triangles that are formed are similar triangles, okay? This is optional, but it's because, okay, this mirror that he's looking into, okay, so you've got this angle here at which he's looking into the mirror, and in the mirror, okay, that angles of reflection are actually the same, okay? That's a property of when you look into a mirror, okay, or if you look into, it's how light works, okay? So as light travels, so, you know, from the mirror to your eyes, okay, as you look into that mirror, when you reflect through a mirror, you've got that same angle coming the other side with the light rays, okay? So because those angles are equal, that means these angles are also equal, okay? So then you've got these two corresponding angles. You've got these corresponding right angles, okay? And then, so according to triangles, I know that these angles then would also be equal as well. So you've got these two similar triangles, all with the exact angles inside. And so that's how actually you know that the two triangles are similar, but you're not required to do this in the question because actually you're told already in the question to make it a little easier that the triangles formed are similar, okay? But according to physics, they have to be similar. Okay, as long as this person is angled in a way that, you know, when he's looking into the mirror, he can actually see the top of the building, like it says in the question. All right. So now that I've proven that those are similar triangles, let's just draw it again. Okay, and so it's obviously not to scale, but so how Ryan has set this up is that we explained that the mirror is 10 meters away from the base of the building. Okay, and that he is standing 0.63 meters away from the mirror. And we know his eyesight is 1.76 meters from the ground. Okay. So then what is the height of the building according to similar triangles? Well, I know that because these are such similar triangles, I have to multiply this number by a scale factor to create this number, okay? So in other words, 0.63 multiplied by a scale factor k creates 10, okay? So then I can express K as equal to 10 divided by 0.63. You're welcome to simplify this if you like, okay? Or you can just put it into your calculator straight in, as is, okay? But it's the same as dividing 10 by 63 hundredths, okay? Which would be the same as multiplying 10 by 100 over 63. So we actually have this scale factor of 1,000 to 63, okay? That's optional, you don't have to do that. You could just type this into the calculator, okay? But I'm gonna use this exact value. So that means this dimension, the height of Ryan, you can multiply it by 1,000 over 63, and that is going to give you then the height of the building. So the height of the building can then be found by this ratio of 1,000 divided by 63, multiplying by Ryan's height of 1.76. Okay, and so that's going to give you the correct answer. So let me have a look at the chat box, see if anyone came up with that answer. Oops. Oh, there's my computer trying to get in the way here. My apologies. There we go. Okay. So someone's given me an answer of 28 meters. That could be an exact answer, actually. Oh, it did say round your answer to the nearest meter, didn't it? Okay. So why don't I use my calculator to work that out? So just using my computer calculator, 1.76. I'm multiplying that by 1,000, and I'm going to divide that by 63. And yeah, I get 27.94, okay? But then rounding that to the nearest meter, as the question instructs, we get this approximate height of the building being 28 meters. Okay, so it's actually not that large a building, okay? Great, so that's a great application to this concept of similar triangles and similar figures. Okay, so now, oops, I don't want to share it, I want to present it. So now we're going to look specifically at similar triangles before we finish today's lesson, okay? So when we look at similar triangles, there are 4 tests actually that you can use to determine whether or not a triangle is similar, okay? And the 4 tests are, you can remember them by these letters, AAA, SSS, SAS, or right H, or RHS, okay? So the AAA stands for angle, angle, angle. Okay, SSS stands for side, side, side. SAS stands for side, angle, side. And RHS stands for right angle, hypotenuse side. Okay, so I'm going to look at each of these 4 examples. So AAA is 3 angles. So if you have 3 pairs of equal angles, then you know that the triangles have to be similar. So say in the first triangle, I had 10 degrees, 50 degrees, this isn't to scale, and 120 degrees, okay? So they all add up to make 180, okay? If you've got the same angles over here, okay, it doesn't matter what the side lengths are, okay? You know, so it doesn't matter. You know automatically that they will, there'll be that one scale factor that goes from one triangle to the next, that these have to be similar triangles because they're not only the same shape, but because those interior angles are all the same, you know, one triangle is then just going to be either an enlargement or the shrunken down version of the other, okay? So if you've got 2 triangles and their angles inside are both equal, okay, then you can automatically say they are similar triangles. Okay, the next test is side, side, side. Okay, and so we've actually looked at an example of this already. So when the 3 pairs of sides are all in the same ratio. So that's that concept of scale factors. Okay, so if I've got, oops, I don't want to go to the next one yet. Let's look at an example. Okay, if I have 5, 9, and 10, let's do a really simple case, 50, 90, and 100. okay, I know that these have to be similar triangles, okay? It doesn't matter that I don't know what the angles are inside the triangle, but actually I know that for similar triangles, these three angles will equal each other, okay? These three angles must match, okay? But because I don't have what those angles are, okay, you know though that they are going to be the same because those three pairs of sides are in the same ratio, okay? So the 10 multiplies by 10 to make 100 in this case, the 9 multiplies by 10 to make 90, and the 5 multiplies by 10 to make 50, okay? So we've already looked at an example of this today, of this side ratio. The next is side angle side. So we haven't looked at this in too much detail, okay? So with the side angle side, two pairs of sides in the same ratio and then an equal included angle, all right? So if I look at 9 and 11, for example, okay, and then this matches maybe, let's look at 18 and 22, okay? If I've got only the two pairs, okay, of corresponding sides, but then I don't know what this third side is, okay, and I can't work out that third side because these aren't right angle triangles. I can't use Pythagoras' theorem, okay? So if I don't know what that third side is, but I know these angles are the same, okay, so you have to look at the included angle, right? So when you've got a side and then an angle that, you know, makes between those two line segments, okay, you have to have that side, angle, side. That's why it's written in this order, side, angle, side, okay? Those angles need to be in the same position, all right? They need to be squeezed between the two side lengths. Then you can say these triangles are similar triangles, okay? And so then because they're similar, if you then have the first side, 20 or something, you could then work out the other side as well, okay? So that's an example of sine angle side. And then finally, that fourth test was the right angle hypotenuse side test, okay? And so it's because of Pythagoras' theorem that we have this test, okay? So if you've got a right angle triangle, okay? So you know the hypotenuse, right? And you know one other side length. Well, then you know these two triangles have to be similar, okay? And that's because this angle is going to be the same, okay? And then these two angles are going to be the same, okay? And actually trigonometry is based on this concept of similar triangles, okay? So I might talk about that briefly. So you can use Pythagoras, right, to work out that for this specific case, the 4 and the 5, you know, you've got that missing measurement of 3 meters, and for the 8 and the 10, you've got that missing measurement of 6 meters, right? So then because of Pythagoras' theorem, you could use side, similarity to prove that these two right angle triangles are similar. Okay, and so because those right angle triangles are similar, that means they have those matching 3 angles. So note that when I consider the base and the hypotenuse 4/5, okay, it's equal to that same ratio of 8/10, comparing that adjacent side length to the hypotenuse. And so this what bases trigonometry, which you'll later learn, is cosine of theta, okay? So because the ratio of 4/5 is equal to that ratio of 8/10, that's what makes this angle the same, okay? And you can actually use your calculator to find that angle, okay? And it will be equal to the cosine of theta, all right? And then so sine of theta works with the side length that's opposite the angle, not adjacent to the angle. So you're going to learn more about this later in the year if you haven't learned about it already. Okay, it's called trigonometry, but it's based on, I want you to remember similar triangles. That's why trigonometry works. Okay, that's why when you enlarge a triangle, okay, those angles stay the same because those side lengths in the right angle triangle form that same ratio. Okay. All right, I think that's all for my notes. Yeah, so now we can go do some more worked examples before we finish for today. Oh, we've only got a couple of minutes. Okay, so then I better hurry up and hustle. I've only got a couple of these I can go through. I've done that one. Yeah, okay, so here's a good one. So consider these two right-angled triangles in the diagram below. Are they similar? Yes or no? Okay, so you've got to give me the right answer and you need to choose the correct multiple choice. If they are similar, how are they similar? Okay, so Remy has given the correct answer. They are similar because it satisfies the RHS test. Okay, so it is a right angle. Okay, we have this hypotenuse. So 7 to 21 is a factor of 3. And then we have one other side length. So 4 times 3 is 12. Okay, so we've got the hypotenuse, a side, and a right angle. So yes, these triangles do have to be similar according to the right angle side test. Great, we can go do another one. What about these two triangles? Are these going to be similar? Yes or no? If yes, how will they be similar? So this one is tricky, okay, because I have the two side lengths, right? 15 and 24, okay? Yeah, 5 times 3 makes 15 and 8 times 3 makes 24. But for side angle side, I actually need the included angle, okay? And I don't have that angle in either case. So without knowing what this angle is here, okay, or here, I can't then find that missing angle. So actually, it's not known, okay? They could be similar. They could be, but we don't know. There is not enough information. So we actually have to choose option F, okay? So in that particular case, because the angle wasn't the included angle, okay, even though the sides looked like they could have that same scale factor, we were unable to determine whether they were similar or not, okay? So good pickup on Remy there in the end. You got the answer right. Well done. Okay. Now this one, on the other hand, okay, are these sides similar? Are these triangles similar? Yes or no? So this is funny. We've got AAS, right? Angle, angle, side. I don't have 2 sides or 3 side lengths. And I don't have the 3 angles. Okay, so are these triangles going to be similar? So some people actually do give AAS as a test for similarity. So I haven't given that to you today, but technically in a triangle, yes, AAS does give a similar triangle. And there's a very simple reason for that. It's really nothing to do with the side length, okay? It's that with these two angles, 63 and 28, okay, I know that's going to add to 91, right? And so then this angle then has to be 89, and it's going to be the same in both those triangles, right? So when you have 2 equal angles in a triangle, you really have 3. Okay, you really have those 3 equal angles because you can just work out, because all triangles have the sum of their angles must make 180 degrees. Okay, those 3 angles add to make 180, so then you know that missing angle is going to be 89 in both. So actually, you can say yes according to AAA, angle, angle, angle similarity. Okay, but in some textbooks, you will get AAS as a similarity test, and that's because it's the same really as AAA. It's not really anything to do with the side. 24 and 29 don't look similar, okay? You'd have to multiply 24 by, okay, is that even the correct dimension between 89 and 28? Yes, it is, okay? So between 89 and 28, I've got 29. And then in the second triangle between 28 and 89, I've got 24. So actually I'm multiplying 24 by 29 over 24 as a scale factor to get 29. Okay, so yes, they are similar. Great. Yeah, we've got time, I think, for 1 or 2 more questions before we finish up for today. Let me see if I can find something a little harder for you guys. I think some of these last ones are a little trickier. Yeah, here's a good one. Okay, so consider the following triangles. Which 2 of the 4 triangles would be similar? Okay, so we have to select 2 correct options here. So it looks tricky, right? Because the angles, if you look at 80 and 43, 81 and 42, 81 and 56, and 81 and 57, there's no 2 identical angles there, because if you've got those 2 angles, then the third angle will be the same, right? So you've actually got to do a little bit of maths to work this one out. It's not so easy. You might look at this and think, oh, yeah, no, they're not similar. None of them are, right? But you have to work out that third angle in all the cases, right? So looking at case 1, 81 plus 42, okay, that's going to be 123. So then that missing angle would have to be 57. Okay, so now I've got 81, 57, and 42. That matches option D, 81, 57. So that missing angle would have to be that yellow one, 42. So actually triangles A and D are similar. Okay, so if I come to the triangle B, 81 and 56, okay, 81 plus 56 would make 137. So then that other angle would have to be 43. Okay, but then in looking at triangle C, I have 43, but I don't have 81, I have 80, okay? So then that would be 57, that other angle, not 56. So actually, yeah, the 2 similar triangles are A and D, okay? So you've got to select A and D as the correct 2 triangles. So you have to work out that third angle to then use angle, 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 similarity, AAA. Okay. And so, yeah, in part B, it says which similarity test does this pass? Well, it actually passes AAA because you've only got the 1 side length. Okay, so it's AAS in some textbooks, but we can use AAA. Okay, same thing. Okay, I think we're almost, let's do one more hard one and then we can finish. These are really good ones, actually. Let's do this one. I like this one, and then we'll finish. Okay, I'm running a little over time, but this is the last lesson, so we might as well. Okay, so consider the following diagram. Are these triangles ABX and CDX definitely similar? Okay, yes or no? So Remy, you've given the answer of yes. Do you know why they're definitely similar? You can write no if you don't know. But if you know, please write it in the chat box. Because of the angles. Yes, the angles are equal, but how do you know they're equal? The lines are continued. Yeah, yeah, Remy's just written in the chat box that the lines are continued. It's because actually these parallel lines, right? So there's this rule for parallel lines where if you have a transversal, so a line that joins, okay, those 2 parallel lines, there are some rules, okay, like the alternate angle theorem, where this angle and this angle are going to equal, okay? And so if I look in this example, I know then that because of these 2 parallel lines, this angle and this angle are going to be the same. Also, because two parallel lines, if this is my transversal, I know this angle and this angle are also going to be the same. And then so by knowing that they're both triangles, okay, you then know that that third angle is also going to be the same. Okay, so yes, we have this angle, angle, angle similarity where you can use those transversals through parallel line theorems to determine those three angles are equal. Also consider that vertically opposite angles are also equal as well. So because it's those same two lines, I know those angles are equal by that theorem as well. So yes, actually, these triangles are definitely similar due to angle, angle, angle similarity. So you can write that as option A. Okay, so now we have a question to answer, our last one before we finish. Okay, let me just clear the board. So given that length AB is 6, what will then the length of CD be? Okay, so let me just scroll back up. So I'm just being told that length AB is 6. So then what will length CD be as a result? Okay. So remember, this angle is equal to this angle is equal to this angle, okay? And then this angle here is equal to that angle there. So 6 is opposite the same angle as CD, okay? So if you can find then the scale factor, right? So then actually opposite the first angle is 4, and then opposite that same angle is 24. So then you can use that scale factor that 4 times k is equal to 64. Okay, so that means, oh, sorry, not 64, 24. That's a 24, right? So that means that scale factor must be 6. Okay, so then that we can then multiply AB by 6 to create length CD. Okay, so the answer is going to be 6 times 6, which is 36. Okay, so we can write that in. 6 times 6 is 36. Great. So that's that other concept of similar triangles. Okay, so that's it. Now you can go into Mathspace if you've got access to Mathspace at your school. And you can now work through some of those questions in chapter 4 from the Year 9 textbook. Thank you guys for all joining me, and for any of you watching the recordings at home, thanks for watching. My name's Daniel. It's been an absolute pleasure. I've enjoyed being back in the classroom and teaching you all. And although, yeah, I would have liked to have seen a few more faces, I understand that now that people are coming back to school, there's just really no need for this anymore. So yeah, we can finish. All right. Lovely meeting you all. Okay. Take care. All the best in the rest of your studies. Okay. And yeah, maybe I'll see you around.